Hi, everybody, and welcome to this week's edition of Communications in NLA. And now that our seminar series is coming closer to an end, we decided to actually have talks by two of our organizers today, and it's therefore a real pleasure for me to announce talks by Davide and Jemima. As usual, you can ask your questions either in the Zoom Q&A or in the YouTube chat. Today, the Zoom Q&A will be monitored by Min Hong. Hi, Min Hong.
Hi.
And the YouTube chat will be monitored by Hussam. Hi, Hussam.
Hello.
And now, as I said, it's a real pleasure for me to announce the talk by Davide Palita from MPI Magdeburg, who will talk about the short-term rational Lanczos method and applications. So, Davide, please go ahead. The stage is yours.
Thank you very much, Marcel, for the introduction. Let me share my slides. And I believe you can see it. Otherwise, let me know. So today I would like to talk about the rational Lanczos method and some application. This is a joint work with Stefano Pozza from Charles University in Prague and Valeria Simoncini from Bologna. I believe we all know what a rational or a block rational Krylov subspace is, and given a matrix A and let's say a block vector B and a set of shifts, we can define the block rational Krylov subspace in this way here. So it's the range spanned by the columns of this matrix here. And it has been shown that the rational Krylov subspace is indeed a very effective tool for like many different tasks. But whatever we need to do, we always or almost always need two different ingredients. One is this matrix QM here that represents an orthonormal basis of our subspace, and the other is the projection of our coefficient matrix A onto our subspace, onto the computed subspace. And what we did is to try to come up with a rational Lanczos method that is able to compute these two tools without storing the full basis QM. So this one way to construct a rational Krylov subspace, it's by rational Arnoldi, and this is basically the most common way to construct this subspace. So we start by orthonormalizing the basis block, the starting basis block B, and then we compute explicitly the projection of A onto the current subspace, and then we start the loop as usual. And you can see here at each iteration we have to solve a shifted linear system. We have a rational Krylov subspace, not a polynomial Krylov subspace. So we need to solve a shifted linear system. We orthogonalize, basically here we're doing Gram-Schmidt, and then we update the projection of A onto the subspace. So we update and we compute this Tj plus 1 here. And we know that by employing the rational Arnoldi method, we come up with an Arnoldi-like relation in this that can be written in this form here, where, as usual, underline H is the matrix stemming from the Gram-Schmidt procedure, while Km, underline Km, is given by this matrix here. So you can see that if we consider standard Arnoldi, so we want to construct the polynomial Krylov subspace in place of the rational Krylov subspace. So we can consider all the shifts to be all infinity. Then we retrieve the standard Arnoldi relation because Km is the identity. So we can see rational Krylov as a sort of generalization of a polynomial Krylov. And we know that when A is symmetric, Arnoldi, polynomial Arnoldi, basically reduces to the Lanczos method. So we don't need to perform a full orthogonalization. We can store only 3 basis block vectors, let's say. And the computed basis is orthogonal in the Saturn method, even though we don't perform a full orthogonalization. So one may think that rational Lanczos, since we can see rational Arnoldi as a generalization of of polynomial Arnoldi, maybe rational Lanczos is again a generalization of the polynomial Lanczos. Because when A is symmetric, then also any shifted version of A is still symmetric. So we may want to mimic the polynomial Lanczos to design a rational Lanczos. So we could orthogonalize with respect to only the last two basis block vectors. So we don't perform a full orthogonalization, and we store only these two last basis block vectors. But unfortunately, it's not this straightforward. And I would like to see with you why this is not the case. So in case of polynomial Lanczos or polynomial Arnoldi, we know that since we're employing Gram-Schmidt and Arnoldi, the projection of A onto the subspace is upper Essenberg. And actually, in this case, in the polynomial case, the projection of A, so the matrix Tm, is equal to the matrix HM. It's actually the same thing, is equal to the matrix that stems from the orthogonalization procedure. So this means that if A is symmetric, then also HM must be symmetric. But if HM is both upper Essenberg and symmetric, then it must be tridiagonal or block tridiagonal. So this means that the basis blocks, so here Qj transpose Qm, they are orthogonal without enforcing this orthogonality. So that's why we can avoid performing a full orthogonalization. But in the rational case, the matrix is Tm and Hm. So the projection of A onto the subspace and the matrix that stems from the Gram-Schmidt procedure are not the same. If you remember the rational Arnoldi relation, we also had that matrix Km that plays a role. So if A is symmetric, this doesn't imply that also HM is symmetric. And here you can see the sparsity pattern of a matrix HM. Here we consider this tridiagonal matrix as A, so of course it's symmetric. We run rational Arnoldi for 25 iteration, and this is the matrix HM that we get. So of course it's upper Essenberg, but it's not tridiagonal. So rational Lanczos is not just a truncated version of a rational Arnoldi. We cannot just say, okay, let's avoid performing a full orthogonalization and then we get the method. This is not the case. We need to make use of orthogonal rational functions, and what I'm going to say here, it can be found also in Stefan Guttel's PhD thesis from 2010. So if our coefficient matrix A is symmetric, and we consider a set of real shifts that can include also infinity, and we have a spectrum measure E, then we know that we can compute a basis here of this Hilbert space that is orthogonal with respect to the inner product defined by E, and we can compute this basis by a 3-term recurrence, and this is the 3-term recurrence that we can employ, where alpha j and beta j are scalars for all j. So when you think about a short-term recurrence, a 3-term recurrence is exactly a short-term recurrence, the short-term recurrence that we're going to use also to design a rational Lanczos method. And this is the algorithm you can find in Stefan's thesis. And so again, here we consider the easiest case where B is just a vector, but it's the same also when B is a block vector with more than one column. So we normalize this vector and we start the loop here. If you are familiar, if you remember what I told you about rational Arnoldi, there we have to solve a single linear system at each iteration. Here in rational Lanczos, or better in Stefan's implementation, we need to solve 2 linear systems at each iteration. And that was probably the main reason why Stefan basically says in his thesis that maybe this method is not that competitive because of this drawback. Like from a computational point of view, of course, we need to solve 2 linear systems in place of only 1. But we were able, by simply rearranging the terms in this iteration, to come up with a new implementation where only 1 linear system with 2 right-hand or multiple right-hand needs to be solved. And we all know that solving a linear system with multiple right-hand, let's say in this case 2 right-hand sides, is better than solving 2 linear systems maybe sequentially. For instance, if we want to employ a sparse direct solver here, we need to read the sparsity pattern of the coefficient matrix only once. If we want to employ an iterative method, again, block method, preload block method, for instance, usually perform better than the same method run twice or multiple times. So this is a somehow better implementation from a computational point of view. So we are able to compute our bases by this 3-term recurrence without storing the old basis. But if you remember, the second tool we are interested in is also the projection of A onto the subspace. And in rational OLD, we basically compute an explicit projection. So again, we need the old basis to accomplish this task. So if we wanted to compute an explicit projection, we would need to compute something like that. And so you can see here, as I told you again, we need all bases. So we cannot afford computing TM in this way, because again, by running rational Lanczos, we don't have at hand the whole QM. But fortunately, we managed to come up with a different expression for TM, or for like updating TM. Remember the rational order relation again in this way, and this can be written in this other form here, where Km and Hm, as usual notation, are just the leading submatrices of underline Km and underline Hm. So if we pre-multiply this expression by Qm transpose, we get this expression here, and if we solve from the right by Km, so we need to assume that Km is not singular, but this is the case if the space that we have computed so far is not A invariant. We come up with this expression here. But unfortunately, again, this vector Wm that is defined here, again, you can see we have the presence of the old basis Qm. So we need to come up with a different expression for Wm, and this is what we've done. So if we define Um in this way, so this vector here, and eta m in this other way here, so Tm plus 1 can be written in this way here, and it's basically the rational Arnoldi relation that we had in the previous slide. So if we compute just the matrix product, we end up having this relation here for Um transpose. So this means that Wm, that is just as this vector Um multiplied by this scalar here, can be written in this form. And everything that we have in this expression here is actually available at iteration M, because we have beta M is just one of the scalars coming from the short-term recurrence. Zeta M is just the current shift, Cm, sorry. Eta M is this scalar here that we have, because we have the last basis vector Qm plus 1. And of course, we have the matrices Km and Hm. Okay, so we were actually able to compute Tm without storing the old basis Qm. Okay, about applications, well, as also like its polynomial counterpart, also rational Lanczos can be used very successfully in the numerical approximation of bilinear and quadratic form. So we have a matrix A, a function f that is well defined on the spectrum of A, and we want to compute something like this here, where u and v, for instance, are vectors or block vectors. Doesn't really matter. And we can find like expressions like these in network analysis, regularization problems, electronic structure calculation, solution of PDEs, Gaussian processes, and many more. But an application that I would like to show you today is the computation of the H2 norm of a linear time invariant system. So we consider this system here, where A is a stable matrix, so its spectrum is contained in the left open plane, and B and C are respectively like tall matrices, and so few columns B, and like a fat matrices C, so few rows. And the H2 norm of this system is defined in this way here. These two formulations are equivalent. In this case, Q and P are the so-called controllability and observability gradients. So they are the solution of these Lyapunov equations. Okay. So what we could do is to apply a projection method to solve one of these Lyapunov equations. So for instance, we want to compute P, or better, we want to compute an approximation of P that here we call PM. And if we apply a projection method, we usually compute an approximation in this form here. So QM, YM, QM transpose, where QM is represents a basis of our favorite approximation space. And of course, in this case, it's going to be the rational Krylov subspace. And if A is symmetric, we can compute QM by rational Lanczos. This is what we want to do. And YM is a small square matrices that is computed by solving the projected problem. So we have our original problem, we project this equation onto the current subspace, and we solve the projected equation. So we compute this matrix YM, and this is it can be shown that is equivalent to imposing a Galerkin condition on the residual. Okay, so it seems that to have, if we need the old PM here, the old approximation, we need again the old basis, and this is something that we don't want to do. But fortunately, since we don't want to we just want to compute an approximation of the H2 norm, so that's our goal. We don't want to have an approximation of the solution of the Lyapunov equation. The main goal here in this case is to compute an approximation of the H2 norm. So this is how we would compute the H2 norm of the original system. So if we replace P by PM, its approximation, then we can write this here, this relation here. So instead of storing the old QM, we just compute this matrix PM on the fly, so we can avoid storing the old matrix, the old basis QM, and this is going to be our approximation. And it can be shown that this is actually the H2 norm of the projection LTE system. So the system, the reduced system, because here we are in the modular reduction framework, the reduced system that is obtained by projecting the original LTI system onto the rational Krylov subspace that we computed. For a stopping criterion, so also here we need to check something that doesn't need a value, that doesn't need the O basis to be computed. So we decided to basically check how the current approximation differ from the previous one, or like from the quantity, the H2 norm we computed like S iteration before the current iteration in a relative manner here. And so again, here we don't need the O basis to perform this convergence check. Example, I don't want to give you details about this example. It's just, you can find it on the MOE wiki. And since only one comment is not a very big example. So the matrices involved in this example are not huge. So we're actually able to compute the H2 norm of the full system. So we don't, in this case, we didn't need to go to reduce only to the reduced system, but we were able to compute also the H2 norm of the full system. So we are able also to check the error that we compute by approximating our H2 norm. So we run both rational Noldi and rational Lanczos, and both these methods are stopped whenever the relative distance between the two consecutive approximation is less than 10 to the minus 8. And you can see here that both methods, rational Lanczos and rational Noldi, need to have iteration. So they basically, even though they construct a rational closed subspace in a very different manner, they end up constructing the same exact space, because here we're employing also the same shifts. So what we did is we ran once rational Lanczos and we got the shifts. Again, rational Lanczos with this shift and rational Noldi with this shift. And so we end up constructing the same exact space. You can see here also from a computational point of view, we get very similar results. So it seems that thanks to our new implementation, it's not true that rational Lanczos is not competitive in terms of computational time when it's compared to rational Noldi. And also from an accuracy point of view, they get basically the same exact results. Here, this is the relative error, and we achieve basically the same error. So to conclude, we managed to design a more computational appealing implementation of rational Lanczos that is competitive with respect to rational Noldi in terms of both accuracy and numerical performance. But at the same time, we get a lower memory requirements because we don't need to store the whole basis. Different applications, of course, any kind of quadratic and bilinear forms. But if you want to think about more model reduction related applications, we also have the H2 norm. We may want to compute the H2 norm of also certain parametric LTI systems and also QR feedback control. In the preprint that you can find on arXiv, we also have some preliminary consideration on the stability of this method, and as its polynomial counterpart, also rational Lanczos may suffer a sort of loss of orthogonality in finite precision arithmetic, but these are very preliminary considerations, and further studies in this direction are definitely needed. Difficult, tricky, but absolutely needed. And with this, I'm done, and I thank you for your attention. Thank you very much.
Thanks a lot, Davide, for the great and very interesting talk. Min Hong, do we have questions on Zoom?
Yes, there's a question from Neil Van Barkhart. In the derivation of the short recurrence relation, which also appears in Stefan Gall's scissors, as you stated, you restrict the possible poles to real poles. Would it be useful to also be able to choose complex poles in your setting? And would the same proof hold for the complex case? Thank you.
Well, since A is symmetric, its spectrum is real. So I believe, I don't know if it really makes sense to consider complex shifts. We did a look into that, since basically Stefan method worked really well. And I can't tell you if the proof would work the same. Maybe yes, but there are probably some technicalities that need to be adjusted. But I believe since asymmetric, the spectrum is real, why do we want to go for complex shifts? That's my question. Also when we run rational Arnoldi and asymmetric, we usually restrict ourselves to real shifts.
Okay, do we have further questions on YouTube, Hussam?
No, we don't. That's all, I think.
Okay, then thanks again, Davide.
Thank you.
And now we come to our second speaker of today, Jemima Tabbert, who will talk about new preconditioners for the saddle point formulation of weak-constraint 4D var. So Jemima, please go ahead.
Right. And hopefully my slides are okay. Cool. So thanks very much for the introduction. I'm going to get straight into the problem of interest. I want to find the state x0 that minimizes an objective function that looks like this. And so the context I'm thinking of is data assimilation for weather prediction. So I want to find an x0 that's close to a prior state, so a previous forecast, some observations over a time window, and then my evolved state with a nonlinear model. And we've got operators M, which is our model, and H, which maps from state space to observation space that can be nonlinear. But in practice, I'm dealing with really huge problems for weather forecasting. I want to solve them quickly. So what I typically do is solve a small number of outer nonlinear loops and a much larger number of inner linearized loops. And so one way we can approach this is just by considering a linearization of this objective function, in which case we have a symmetric positive definite least squares problem, so we can just use a conjugate gradient method. But what I'm going to talk about today is instead rewriting that as a saddle point problem. So you might wonder why this is a nice idea. If we look at the dimension of these matrices, S, the size of the state, can be of order 10 to the 9, P can be of order 10 to the 6. I've basically just rewritten a much bigger matrix system that's now indefinite, so I can't use conjugate gradient anymore. However, there are some advantages to this approach, namely that instead of a lot of sums like I had in the objective function form, I now have a load of block diagonal matrices, which are much more parallelizable. And one thing I don't have is very much time, but I might have access to a large number of processors on a supercomputer. So the advantage of this saddle point approach really comes from this inherent parallelism. So if you don't know anything about the problem, I'm basically looking at preconditioners for this system here. And so the matrices all come from that objective function I showed you earlier. And one of the main ones of interest in this talk is going to be this L operator. So this contains the identity on the diagonal. And then under the diagonal, we have our linearized model operators that will evolve our state that we're looking for, delta x, from the beginning of my time window to the end of my time window. Thankfully, there's been a lot of previous work in the literature on saddle point problems, but it doesn't always apply to problems of this type. And that's because within this saddle point system here, our operator L is really one of the more complicated things we're dealing with, whereas a lot of work for saddle point systems, the 1-1 block is quite hard. So we have challenging things to deal with in almost every term. Additionally, as I said before, the advantage of this approach is really the parallelization that we can achieve. And so that means that we need to design preconditioners that are still parallelizable. Otherwise, we're just solving a really big, expensive system in serial, which is bad. So I want to propose some new preconditioners that ensure parallelism and will help with some of the terms in this matrix. So I'm going to start by considering some standard approaches, namely the block diagonal approach and the inexact constraint approach. And so here, anything with a hat is going to be approximated. And in this talk, I'm going to focus on R, which is the observation error covariance matrix, and L, which contains the model information. So we also have this S appearing, which is our Schur complement matrix. And I'm going to immediately approximate that by neglecting this second term and using my approximation L hat here. So even in the block diagonal case, the L hat approximation is appearing here. And the reason I've considered these two choices of preconditioners is that the block diagonal, it's symmetric positive definite, so we can use min-res and we can develop some theory on the convergence in terms of the eigenvalues. So that's going to help us design some new choices of R hat and L hat with a theoretical basis. However, in practice, the inexact constraint method is found to perform really well, but it's almost impossible to say anything theoretically unless we are in the really unrealistic setting where we approximate everything with the exact matrices. And I'll tell you why that's a bad idea in a minute. So we expect this to perform well in practice, but we're hoping that the theoretical insights from the block diagonal preconditioner can give us some good ideas of useful preconditioners for this setting too. So to start with, why do we need to approximate L? Can't we just use the exact inverse? And I have my L matrix here. We can see it's really got a lot of scope for parallelization. However, when I invert, I fill in this lower triangular matrix. And what's worse, I fill it in with matrices that have lots of products of different linearizations of my model matrices. So this is not parallelizable. And if I use this, I've ruined all my nice structure that I had before. So what we need is an approximation L hat that is parallelizable in the inverse as well. And so one standard approximation that's used is we just neglect all of the model information, which gives us the identity, which when we invert it is the identity, which is very parallelizable. So this is quite a simple approach, and it doesn't include any model information. So that means that irrespective of what my model is actually doing, I'm going to have the same preconditioner. But we wondered, can we actually do better if we include some model information, but ensure that we still have some parallelization? And the answer is yes. Okay, so our new proposal looks like this. I have my original matrix LM, and I have a parameter K that I choose. And K tells me how many blocks in my matrix to delete. So if I have K as 3, I'm going to delete every third entry. So I delete the third one and the sixth one. If K is 4, I delete the fourth one and so on. And what this means is that if I delete this M3 term, in my previous matrix here, anytime M3 appears, the product's going to be set to 0. So that means that in my inverse, I'm going to end up with a block diagonal matrix, and the size of the blocks and the number of serial matrix products that have to be evaluated is going to be controlled by this parameter K. So this is really parallelizable. I know in advance by choosing my value of K how many blocks there are going to be. And there's also some nice links with the preconditioners I introduced before. If I pick K as 1, that means I'm going to skip everything and I just recover the identity again. And if I pick K as n plus 1, then I won't skip anything and I'll just get my original matrix L back. So there's going to be a balance here between including more model information, which will help me hopefully reduce the iterations, but not having so big blocks that I can't exploit the parallel structure anymore. So we expect there's going to be a trade-off, and our feeling is that small k, so perhaps 3 or 4, is going to be the most benefit between including some information, but ensuring we can still have a lot of blocks. And so I'm going to focus today on theory for the case k is 3. So I want to compare my new choice to the existing choice. And one way I can do that is by considering the eigenvalues of this product here. So in order to make my life a bit more simple, I'm going to consider a more specialized case. So my linearized model is going to be the same every time. It's going to be symmetric, and my eigenvalues are going to be bounded between -1 and 1. So if I do this and use L0, which is the identity, the eigenvalues are bounded above by 4. If I use my new preconditioner with k as 3, so I'm deleting every third term, my maximum eigenvalue is bounded above by the number of the blocks, or 8. So even if I have a large number of blocks, or I increase the size of my state, we know that this maximum eigenvalue is going to be well controlled, although you might notice that 8 is larger than 4. However, we also have some really beneficial properties in terms of unit eigenvalues. So we have that if we use this preconditioner with some model information, we're going to get many more unit eigenvalues than we'd expect in the case where we're using the identity. So we have at least 2 times the number of state variables, and we have some additional blocks coming in which depend on the number of blocks that we have. And basically, as we increase the number of blocks, this value of I is going to increase. So this is really promising for a preconditioner. The theory I presented here is specific for the case k is 3, but we can get similar results for larger values of k. In particular, this maximum upper bound on the maximum eigenvalue will increase as we increase k, and the number of unit eigenvalues will also increase. Great. So our next thing we want to consider is the approximation to the observation error covariance matrix. So almost all previous work in this data assimilation setting assumes that R is cheap to invert, and we basically don't need to worry about an approximation because we can just use the exact matrix. But this isn't true for all choices of R. So in particular, satellite instruments often have error covariance matrices that have very complicated structure and are really ill-conditioned. And sometimes you don't use all of the different columns. So that means that we can't invert it on the fly. So we have to have a good preconditioner there. So we're going to consider some new preconditioners that keep some of that in correlation information that's really important, don't require much input from a user, and also have extra parallelism. We're going to compare both against the exact choice of R and also against just using the diagonal, which is obviously extremely parallelizable. So our new approach, I'm going to illustrate with this very beautiful picture that I drew. So here's my covariance matrix that I'm starting with, and we have some blocks of a predefined size. So we can imagine that each of these blocks corresponds to a different instrument. And so we're going to have strong correlations within the block, but we can also have correlations between different blocks. And we want to keep the information that is useful or strong, but if the information is quite weak, we don't really care. So the way we're going to measure that is through a weighted Frobenius norm. So we're going to go through these super diagonal blocks and measure their weighted norm. If it's above a tolerance that we specify, we keep it. So those are the red ones. If it's below a tolerance, we throw it away. And if we throw it away, we get rid of everything else that's in the column or the row above it. When we symmetrize this, we end up with a approximation that is block diagonal. So we've introduced further parallelism. And we also have that within the algorithm, the user can control how many processes they have, so how many blocks to split it into, as well as ensuring that you don't end up in a situation where you get one small matrix going to one block and one large matrix going to another block processor. So this is quite a easy thing to do computationally. It doesn't require much effort. So we want to see if this kind of first order attempt is going to be beneficial as a preconditioner. So we're going to present two sets of numerical experiments. The first is using the heat equation with the Dirichlet boundary conditions. And the reason I've chosen this quite simple problem is because we have a linear setting. So when we linearize, we don't actually have to do anything. Our model is going to be the same every time. It's symmetric, and our eigenvalues are bounded between -1 and 1. So we're satisfying all the assumptions from that first section of the theory. So we hope that our new approach for L is going to perform well here. And because we're in a setting where everything is symmetric, we're going to try using the block diagonal preconditioner with minres. And so here's some results. On the left, we have what happens if we use the identity as the preconditioner for L. And on the right, we have our new preconditioner with K as 3. On the top, we've got wall clock time and the bottom iterations. And as we move from right to left, we're increasing the spatial resolution. So the dimension of our problem is getting bigger. And in terms of the choices of R, the pink one is if we just use the diagonal choice of R. The red one is if we use that block approach I just described. And the cyan one is if we use the exact R. So firstly, we note that if we use our new choice of LM, we get a reduction in iterations compared to using the identity. And this translates into a reduction in wall clock time as well, which is really good because obviously including this model information does increase the cost per iteration. We also see that we really, really need to include this correlated information in the preconditioner. Using just the diagonal information is quite bad, both in terms of iterations and wall clock time, even though it's cheap to apply. And we also see that we basically can't see the red line because it's hiding under the cyan line. And that's really good because our quite rough and ready approach is retaining the same number of iterations as using the exact choice of R and is competitive in terms of time as well. We also recall that we have this block approach, which will allow for further parallelism, but all of these results here are in serial. So we expect further benefit if we exploit that structure in practice. So that was a setting where all of our assumptions are satisfied, but that's not very realistic for real problems. What happens if none of our assumptions are satisfied for the theory? So I'm going to present the second case study, which is using the Lorenz 96 problem. This is a series of coupled ODEs. And the forcing term here gives us chaotic behavior. So it's quite a classic toy problem to consider within the data assimilation setting. When we linearize this problem, we get a model that's different every time. It's not symmetric. The adjoint is not the same as the transpose. And we get that the eigenvalues are greater than 1 if we have enough time steps. So precisely none of our simplifying assumptions are satisfied. This also means that we can't use minres because of the symmetry breaking. So we're going to use the inexact constraint method with GMRes. So here we've got a slightly different presentation. where we have on the x-axis, we're increasing k, so we're including more model information as we move from left to right. The dashed lines here represent the using the identity within L0, and then LM is the solid lines here. Again, pink is if we just use the diagonal of R in the preconditioner, and the other colors are if we use the correlated information there too. So we can see that even with k is 2, so we skip every other block, we get a reduction in iterations compared to using no model information. So it is beneficial even in this setting to include some model information. Again, we also see that using the diagonal choice of R is a very bad idea, but using this block approach is pretty much as good as using the exact R in terms of iterations. If we look at the wall clock time, we see that it's slightly complicated, obviously including this extra information via LM is more expensive, so we do need a bigger reduction in iterations before it becomes beneficial in terms of wall clock time. But k of around 3 to 5, we can already beat the improved convergence in terms of time that we see using it with LM. And again, we really want to avoid the situation where we're not using the correlated information. So this is quite promising because in a setting where we don't satisfy any of the theoretical assumptions, we're in fact using a completely different preconditioner, we get the same qualitative behavior of our new preconditioners, both in terms of R and L. So it seems that this approach is going to be more broadly applicable than the quite limited setting that our theory applies to. So to wrap up on what I've just presented, we proposed some new highly parallelizable preconditioners for the saddle point formulation of this weak constraint 4D bar problem. Our new method for L includes model information, we think, for the first time. Our new approach for R allows us to include correlation information and also guarantees that we have additional parallelism. We find that iterations and wall clock time are improved compared to the standard choices of preconditioners, and not just for the problems where our theory says it should, more broadly. And all of the experiments I've presented have been performed in serial. So if we actually exploited the parallel structure, we'd expect to see even more improvements there. So that's everything I had to say, and I'm happy to take some questions.
Thanks a lot for the great talk, Jemima. Yeah, Minhong, do we have questions on Zoom?
Yes, there's a question from Daniel Krasner concerning parallelization for the block by diagonal matrix. Parallel aims at addressing a similar situation. Parallelization of example implicit Euler in time 9. Would it be possible to carry over ideas from parallel to this setting?
So I'm not too familiar with exactly what goes on with parallel, but yes, I'm sure that there's a way to carry over ideas from that setting to this type of problem. Is my short answer, but I'm happy to discuss further and more details later.
Okay, Hussam, do we have questions on YouTube?
No questions on YouTube.
Okay, then yeah, thanks again, Jemima. And before we end today's session, let me briefly share my screen to advertise our next session in 2 weeks, which will actually be our very last session of ComNLA. And yeah, to conclude our seminar, we will have a joint presentation by Fuzan Hosseini and Eleni Vrachopoulou from NAC, and they will talk about high-performance computing. So I really hope to see you again in 2 weeks. I thank all of you for your attention, and it would be great if you could join us on Gather Now for the discussion. See you. Bye-bye.